you for inviting me to this lecture series. Uh, right now, in this lecture, I want to talk about CFD simulation of a rotameter. First of all, I'd like to introduce myself. My name is Dara Rahmat Sani. I live in Tehran, the country of Iran. Uh, Tehran is the capital of Iran, and right now I'm studying chemical engineering, and I'm in my last semester of my bachelor's degree in the University of Iran, University of Science and Technology. So I guess all of you know that where Iran is, but I'd like to mention it again. Iran is in the middle of Middle East. In the red dot is the Tehran, the capital of Iran, where I live, and we are quite near to India. The university that I study in, Iran University of Science and Technology, is one of the top 3 in Iran, 76 in Asia according to QS ranking, and 500 to 550 world ranking, again according to QS. Okay, my lecture has 3 parts. I will start with introduction, that what is CFD, what is the basics of it, and what is the steps of designing a CFD simulation. And in the next step, I will talk about Rotameter, why it is used, how it's constructed, what its benefits, and what is its faults. And in the last step, in the last chapter, I will combine 2 first parts, and I will talk about designing and simulating a rotameter using CFD. So, what is CFD? CFD is an acronym of Computational Fluid Dynamics, and according to Wikipedia, the easiest sentence that I can find to describe CFD is a branch of fluid mechanics that uses numerical analysis and data structures to analyze and solve problems that involves fluid flows. And it's very common that we have lots of equations that are not linear, and sometimes our physics, our geometry is so complex that we can't solve them analytically, so we need to discretize them, make them linear, and create small cells and solve it numerically for many things. That mostly in modern days we use computers and HPCs to achieve these tasks. Okay. The first beginning question that we need to ask is why we use CFD, why not using analytical ways or experimental ways to find out what is the best design. So I listed 5 most common reasons that we use CFD, and in future slides I will give some examples about them and to make it clear for the audience why we use CFD. But right now, the brief is parameterization. We have to pay more cost for material and deployment. We can deploy it very faster to come up with a case, to come up with a case that we can experiment our designs is much more faster. We have no physical limitations and we have no measuring limitations. I will discuss all of these in a few near slides. For example, I want to start with the physical limitations. I guess all of you know that a few months ago, maybe a year ago, NASA sent a kind of a rover to Mars that had a quadcopter in it, and they made it fly in the Mars atmosphere and take some photos of the Mars. And let's see how they made it. Actually, there's very difference between Earth and Mars. The gravitational acceleration is completely different. the species of the atmosphere is completely different, and now you want to create a quadcopter and you want to make it fly on Mars. So how you want to create a similar situation like Mars, how you want to create a different gravitational acceleration on Earth or a different atmosphere. It's, I guess, creating this kind of tunnel or space to with different gravitational acceleration with different atmosphere must cost you very much, maybe millions of dollars. So experimenting that is very hard. We have physical limitations. But if you use a CFD in our computer, in our case, we are kindly the god of our world. We can change every physics that we want. We can change the gravitational acceleration with just typing a new number. We don't need to create a huge space, a box with many modern systems to create different gravitational acceleration. Or we can just easily change the fluid properties, the gas
Recording in progress.
Gravitational acceleration. We can create different atmosphere completely easy in our simulation. So I think I could make it clear that why we can easily change physical, we can break the limitations of physical situation. Another way to why we use CFD is, let's guess, imagine a centrifugal pump. We want to find out how many blades we should use, what is the best angle, and we are some parameters to define what is the efficiency of our pump, and for this reason we want to find it what is the best design. If we want to do it experimentally, we have to buy materials, design it in a geometry modeling software, right, like SolidWorks, then use that material, use some tools to create to make it that pump, then test it. Okay, so this process takes a time. It will cost you some buying some material and manufacturing prices, and it takes you time, maybe 2 or 3 days for each design. So but if you use CFD, you don't need to use any material. Everything is virtual. You create it, you simulate it, you find the results, and you can put it in a very good loop and parameterize it, and very efficiently change the parameters using optimization algorithms and find the best design. And if you have a good computer, you can rent it. Right now, many companies provide this kind of. Let me share my screen again. I apologize for. I think I was here. Okay. As I said, if you have a centrifugal pump and you want to experiment
Recording in progress.
You want to know, find out which design is the best, how many blades you need to use, or what is the best angle of your blade. So if you want to do it in traditional way, experimental way, you need to use material, construct it, design it, test it, record the results, compare it, and every cycle you take, it may takes you some money to buy the material, some money to construct it, and it takes you time, maybe 2 or 3 days. And if you want to run many experiments it can take you months to find the best result. But in CFD, and if you have a good computer, you just need to parameterize it, and with using optimization algorithms, you can easily change parameters and test your designs. And there are lots of HPCs and companies that provide cloud computing resources, and you can easily run tens or hundreds of experiments and find the best result without buying any material, without any time consuming making and constructing the pump. So, as I mentioned, another limitations that we have on experimental designs is measuring limitations. Imagine an airfoil that you can see in the picture, that you want to see the velocity profile of the air on this airfoil. How you want to measure it without disturbing the air. You want to put a probe here, so that probe is physical, and it will interact with air and change the velocity a little bit. So how many probes you want to use to find the complete profile of velocity? You can't use 100 probes here, and every single place and find all the velocities. You have limitations. But again, in CFD, in the virtual world, uh, there are numbers, they are completely calculated. You can see every single point, the velocity, the pressure, and every number you like. So this is another reason that we love CFD. But after knowing that why we should use CFD, we should know how to properly uh, take the steps of designing a CFD case and make it. As you can see in this slide, five main steps are geometry modeling, physics definition, discretization, or mesh, creating mesh. It's kind of mesh, solving it with different
Recording stopped.
solving
Recording in progress.
Solving it with different algorithms, which algorithm we should use, and process it, and we should make some contour plots, bar plots, streamlines. We want to find, we should make it human readable. Okay. The first step is geometry modeling. It's very, I guess, as mechanical engineers, you have lots of courses, lots of classes that teach you uh, this how to use softwares, how to create a geometry. There are lots of softwares that can be used to design and create a model. You can use SolidWorks, Design Modeler, SpaceClaim, FreeCAD and Solomon, which are the open source versions of CAD softwares. And the system of all of them are quite similar. The next step that you have to uh, define your physics. Most common physics that we mostly define on every CFD case is the momentum balance, Navier-Stokes equations that we all learn in fluid mechanics courses, fundamental of fluid mechanics, mass balance that it is taught to us in the very basic school, higher school, and in in a in university. In some cases, we have heat transfer. We learn it in heat transfer course. That the basic of it is that energy is stable. We it is balanced over any system, and in some cases with reactions or uh, more chemical uh, phenomena. We have mass transfer, and this these equations can expand very much. We have turbulence, modelings, reactions, radiation, convection, uh, many. We have many kind of physics. We need to define. We have to learn what is our problem is, define our physics, knowing the properties, and define the boundaries, which are walls where uh, our velocity gradient is zero. Maybe sometimes we have walls that with fixed temperature. We should define these properties as well. Okay, as I said, in many physics, we have problems with solving them analytically. They are maybe very complex and many uh, physics are involved, and so we need to discretize it. One of the basic discretizations that we learn in Calculus 1 is Taylor series. There are many ways to discretize our problems, but I started in one of the basic one, Taylor series. You have some animations that how Taylor series approximates non-linear problems and make them to linear and polynomial equations that we can deal with them very easily. We can find the derivatives, integrals, second derivatives much easier, and lots of equations that we introduced in previous slide are nonlinear, and with this Taylor series we make them linear and we can deal them very easily. And if you have passed the numerical analysis course, solving those equations numerically is much more easier. So I guess you are familiar with Taylor series equation. It's we can use to find derivatives and change the equation and change the size, find the first derivative, second derivative, and if we include more and more terms, we can have more accurate uh, results. For example, in this equation that you can see in this GIF, um, every term that is added, the approximation is much more nearer to the uh, function that we want to approximate. So after that, you know many different algorithms that we use for solving numerically any equations, and it's a very huge topic. I'm not going to in the detail. I just like to mention the most common algorithms that are used for solving this equation, Navier-Stokes equation, heat transfer, and this kind of equations. Many of them take steps that finding and guessing a pressure for every cell, for every point. Then after that, they will from using Bernoulli equations um, they compute velocity, and after that they start computing other terms like temperature, mass balance, and this kind of things. I'm not going to the topic. It's just an introduction. Okay, the final step is post-processing. Uh, the computer just sees some numbers, they change the numbers, add them up, subtract them, multiply, divide them, but we as humans are not able to uh, deal with this huge amount of numbers. They are just numbers. We can find anything from them. So we need to visualize them, make it easier to read and uh, easier to find out what's going on. So there are lots of plots, ways of plotting, counter plots, streamlines, bar charts, line charts, pie charts. There are lots of ways of visualizing them. And for example, we can find where is the more pressure, where is the least velocity, and we can find it out. One of the most steps that in post-processing after visualization we should take it is validation. We shouldn't forget that we are in a virtual world, and who says our results are correct? How we can find that it's um, valid? We need a way to find out is our results near the real results that if we set even experimentally we have the same result. So most of the time it's a very critical step in CFD cases that we need to validate them. So we should make a simple way, for example, very small airflow, just check few points. Is that pressure and velocity that we computed near the experimental results? We should check it. It's a very important step. And after that, we find that if we find that our equations, our ways, our accuracy is correct, so we can now, after that, we can completely easily do our parameterization and be comfortable that our results will be correct. Okay. So how we noticed the basics, that's how CFD codes work. So how to do it, how we should program it, how to create these equations. There are lots of CFD codes and softwares. Some of them are commercial, some of them are just completely for few universities or companies. But three most famous CFD softwares and codes that we can use, and they provide services, are these three companies: COMSOL MULTIPHYSICS and ANSYS Fluent, that you have to buy a license. OpenFOAM is a free open source code that you can use. There is no limitation for it. There are lots of difference between these softwares, and I'm not going to open the details, what is the differences, but ANSYS Fluent, for very brief overview, COMSOL MULTIPHYSICS is more user friendly, but and less advanced. It's a good start for.
I think the time is ending. You can join back in 5 minutes.
Oh,
It is giving some message. Yeah. 5 minutes you can join back. Okay.
do you have my voice? Do you hear me?
Recording in progress.
Oh,
Yes. Mr. Darasamy, you can start now.
okay. Okay, as I said, there are these three softwares that you can use to run your CFD codes and simulate your physics, your cases, your projects. So In the second chapter, I want to briefly talk about what is rotameter. Rotameter is one of the oldest variable area flow meters. It's very simple. It's made just from two parts. There is a tube that you can see the ruler on it, and it's a floater that changes its place vertically in the tube. Rotometers are very useful for laboratories and research tasks, and mostly we use it for clean fluids without any dust and solid granular things, and it's very suitable for steady flows. It's not very good for flows that their flow rate change very heavily, very sharply. And its benefits that is very simple to construct. It don't need any kind of it doesn't need any kind of electricity, and it's relatively cheap. But it has some problems that you must install them vertically, and their design is completely based on density, and because of that, if you change the fluid type, maybe if you're using water and change it to use oil, you need to calibrate it again. It's completely dependent to the fluid type. Two most important standards that help you and guide you how to design a rotameter are VDI 3513 and ASTM D3195. You can find them easily. I think VDI is completely free. If you search it, you can find it. ASTM, I think you need to buy it. But how rotameters work is very simple. It's a balance on forces of flow on floater. On the floater, it has some mass, so a gravity force it is applied to it. Because the flow of water or flow of fluid from downside to upside, a buoyancy force is applied to floater as well, and because of the flow of the fluid, a drag force will be applied on the floater as well. So if we write them in an equation, this is the equation. W is equal to F plus A. F is the force of the drag. A is the force of buoyancy force, and W is the force of gravity. And it's very easy to compute the buoyancy and gravity force if you have the density of the solid of the floater, density of the fluid, and the volume of the floater. We can compute them easily. So let's combine what we talked today and talk about designing a rotameter with CFD. There are two ways that we can simulate a rotameter. The first and simplest one is stationary simulation. The second one is transient simulation. In the steady state design, it's a little bit complicated, and you have to try and error your design. You guess a position for your mass flow rate for the ball. You guess a position for your ball. You put it there. You compute the drag force. I write it wrong. Drag force. What is drag force? And all of these softwares and codes with just turning on an option will compute the drag force on your ball, on your floater. So you have all of the forces. You have the gravity force, you have the buoyancy force, and you have the drag force, and you put it in that equation and see the equation is correct or not. if it's not near 0, so you have to change the ball position, and you simulate again, and after a while you will find the best position that fits in the equation, and you find that that's the right place for your rotameter, and because you know you manually set the mass flow rate, you can write that height is the uh, that height is the place that you should start your ruler. The transient simulation is a little bit harder. There are ways to do that. One way is to define a dynamic mesh and uh, and define the mass of your floater, and it automatically changes computers the forces and changes the side of your floater. And another way is to define a volume fluid. While you see this, it's a volume of fluid, two-phase, and uh, deal with the solid of the floater as a fluid with very, very high viscosity. So it doesn't change due to the forces. The shape of the floater won't change, and and won't change, and is transient. Maybe sometimes it diverges because of dynamic mesh or this kind of things, but it's more accurate because in stationary fluid we saw that three forces, but we are not sure that they three are the just forces that we have. Maybe you have forces that we don't know, and we haven't computed them. So transient simulation is a little bit harder. It's more time consuming, but it's more accurate. Um, my project hasn't been done yet, and I'm still practicing designing Rotameter, but there are some references. I will send this PowerPoint to the group for more information, for more detail of the journals and papers that I used to create this um, PowerPoint is mentioned in these links. And most of all, thank you for your attention. Thanks from people that who manage this lecture series. I hope you enjoyed. I hope it was useful for all of you.